All right, so last section we're going to take a look at is 5.6, and it's extending everything we've learned about vectors into 3D. So if 2D stuff makes sense, then the 3D stuff is going to be pretty much exactly the same. So everything that we've done so far has basically been in this area. If you think of that as like a box, that's the bottom of the box. Okay, it's called the XY plane. Or if you have like a table in front of you, everything you've done has been on your table. Now, we're coming straight up off the table. Okay, that's the Z-axis. So in 3D, we have a third component we have to add on to everything. All right. X-axis, Y-axis, now we have the Z-axis. When I talk about vectors, I'm not going to use the terms horizontal and vertical component anymore. Because in 3D, I mean, you wouldn't really say X is the horizontal component. It's just, it's one of the components in 3D, but it doesn't make as much sense to say horizontal and vertical. So what I'm going to say now is I'll just say the X component of the vector, the Y component of the vector, or the Z component. The X, the Y, or the Z. Those will be the three. And the way that the coordinate system works is it's called a right-handed coordinate system. And that's because if you use your right hand and your index finger is the x-axis and your middle finger is the y-axis, your thumb is the z-axis. And that tells you the direction of the z. If you use your left hand, what happens is z comes out backwards. So if you line up x and y, with your left and right hand, then your thumbs point in opposite directions. Okay? So if you use your left hand, z would come out backwards. So your right hand tells you the direction of each axis, no matter which way you're facing, all perpendicular. Right? So that's our coordinate system. The other thing is in 3D, you don't have quadrants, you have octants, because there's 8 different sections. If you kind of think of it like this, you could go right, you could go up, and you could come out of the board. You could go right, you could go up, and you could go into the board. That's 2. Right, down, out of the board, right, down, into the board. Left, up, out, left, up, in. Left, down, out of the board. Left, down, into the board. That's the 8 different sections that you could have in 3D. Because 3D is a little bit harder to sketch, you can do all the same things that we've done in 3D, the same thing we did in 2D and 3D. Like you can take a 3D vector, put another 3D vector on the end of it, and draw the answer. So you can do it just like 2D. But drawing in 3D is a lot harder. So when we do 3D, we're not really going to do sketching. We're going to focus on just using numbers, just because it's hard to draw in 3D, at least for me. Okay, so first thing we'll talk about, even more basic than just vectors, is how you find the distance between 2 points in 3D. So this isn't even vectors, right? It's just like you've got a point over here, and then you've got another point over here in 3D, and you want to get the distance between them. So for each formula, what I'll do first is remind you how you do it in 2D, and then right below it, I'll show you how you do it in 3D. Okay, so the first part of every formula today is a review of the 2D, then the 3D. So in 2D, that's how you find the distance between 2 points. That's the distance formula. And the distance formula is really just what formula, written a little differently. Yeah? Yeah, it's just the Pythagorean theorem. You're finding the length of something and square it, the length of something else and squaring it, adding them up and taking the square root. It's just Pythagorean theorem. So in 2D, you'd be given 2 coordinates. Each coordinate would have an x and a y value. Well, in 3D, we're going to be given 2 coordinates, but we're also going to be given a z value. Essentially, you can think of 2D as this part always being zeros. That's basically what we've been doing up until now. we haven't had the z component. Right? It's always been a 0. Now, the z component will not be a 0. So, to find the distance in 3D, all we have to do is take the 2D version and extend it to 3D. To extend it, just look at the pattern that you see with the x's and the y's, and do that same pattern one more time with the z's. So anybody think they know what we're going to have to add onto the end of that formula under the square root to make it 3D? Yeah?
Just like parentheses z2 minus z1 parentheses squared.
Yep. So that is your distance formula in 3D. And that's the Pythagorean theorem in 3D. So you can do Pythagorean theorem in 2D, or you can also do it in 3D. Well, that's the 3D version of Pythagorean theorem. Technically, the 3D version of Pythagorean theorem is the 2D version twice. That's what it really is. You're doing it twice. But that's your formula. Okay, so let's try an example where we find the distance between 2 points that are in 3D. Okay, so there's our 2 coordinates. In 3D, you still call those coordinates, just like you do in 2D. If you want to be more specific, you can call them ordered triples. In 2D, we usually call them ordered pairs. Well, that's an ordered triple. And remember, the reason they use the word order, like ordered pair or ordered triple, is because the order is important. You cannot switch these numbers around and have them be the same coordinate. They have to be in the order x, y, z, alphabetical order. All right, so let's see if we find the distance. Okay, what's the first thing that I should write down so I don't forget it if I'm finding the distance between those 2 points? I did this pretty much for every homework problem I did. I set this up first, then I started looking at some numbers. Yep. Yeah, just write down the whole formula. Just leave blanks for everything you need to fill in. Okay. So we've got square root, and we're going to have 3 differences, all squared and added together. That's how I would do the problem. Set that up first. Okay. Now, we're going to take our numbers and fill them in the correct spots. Okay. What am I going to put inside my first set of parentheses? Yep.
4 plus 1.
Yeah, so it's going to be 4 minus minus 1, which will become 4 plus 1. 4 minus negative 1. Okay. How about my next set of parentheses? What's going to go in there? Yeah.
Negative 2 minus 3.
So negative 2 minus 3. All right. And what about in my third set?
5 minus 2.
5 minus 2. Okay, so now we just do that out, and that's the answer for the distance between the 2 points. So we already said 4 minus minus 1 becomes 4 plus 1. What's 4 plus 1 squared? 25. So we get 25. How about negative 2 minus 3?
Negative 5.
Negative 5. And then when we square that,
25.
that's also 25. And 5 minus 2? 3. And when we square that, 9. So what is the distance between these 2 points? Square root of 59. Okay. If they want it as an exact answer, you leave it like that. If they want a decimal, you just type that in. Any question how to type that in? Okay. So that's the only formula we're going to do today that's not really about a vector. It's just about, here's a point, here's another point in 3D. How far apart are they? Everything else is going to be about vectors. Okay, so first of all, in 2D, how many components does a vector have in 2D? How many? 2, yeah. And we call those the horizontal and the vertical. When we describe them in unit vector notation, we had 2 unit vectors that we used. Does anybody remember the names of the name of the unit vector for the horizontal component? What is it? What's the name of the unit vector that we use in the horizontal component? And we use this letter every time we're doing unit vector notation. Yep, I. What's the name of the unit vector that you use in the vertical component?
J.
We use J. Well, that's the x-axis component and the y-axis component, but now we need the z component. So we're going to need another new unit vector. Okay. I might have mentioned it already, but anybody have a guess what we're going to call that? Okay, we're going to call that k. So in 3D, now you have an I, a j, and a k. So I tells you how many vectors to stack along the x-axis. J tells you how many vectors to stack along the y-axis. And k tells you how many vectors to stack along the z-axis. The top one here is unit vector notation. You can also use the angle bracket, just like we did in 2D. But if you're doing it in 3D, remember you need 3 numbers inside the angle bracket, all separated with a comma. And remember, the A, the B, and the C, those are called the components of the vector. The x-axis component, the y-axis component, and the z-axis component. Okay, and depending on your perspective in 3D, how you're looking at it, horizontal and vertical, those terms don't make as much sense. Okay? Especially if you're looking at it like that. You're looking at it like if this was like a cube in front of you, it's like you're looking at the corner of the cube cut away inside the box. So I'll try not to use the terms horizontal and vertical. Okay, so in 2D, the last thing we talked about, one of the last things, the first day, was we can draw the vector anywhere we want. But if it starts from the origin, that's the most common place to put it. And that has a special name. Does anybody remember what you call a vector that starts at the origin? Yeah?
Position.
A position vector. And it's called exactly the same thing in 3D. It's exactly the same sentence I wrote a couple days ago. A vector that starts at the origin is called a position vector. Okay, and we had a formula for finding a position vector in 2D. So let's review that, and then we'll see if we can figure out the formula to find it in 3D. So in 2D, that's how you find a position vector. Okay, so that should already be in your notes from a couple days ago. To find the position vector, all you're basically doing is taking the initial point and the terminal point, and you are subtracting them. When you subtract, does the order make a difference, or does the order not matter? Yeah.
It needs to be in order.
It needs to be in the right order. 5 minus 2 is not the same as 2 minus 5. If you switch the order when you subtract two things, you will get a different answer, and it will be wrong. So make sure when you're finding a position vector, it's always terminal minus initial. If they don't tell you which point is which, the first one they give you, P1, that's initial. The second point is where it ends, terminal, P2. All right, so now when we want to do that in 3D, instead of just giving you an x and a y for the terminal initial, I'll give you an x, a y, and a z. And how do you think our formula is going to change to find a position vector in 3D? Yeah.
It's gonna be x2 minus x1, comma, y2 minus y1, c2 minus c1.
Right, we're just going to do a comma and put a z2 minus z1 on the end of the formula. So again, for what we did in 2D, extending it to 3D is very straightforward. Just do the same pattern you've already done for the x's and the y's, one more time for the z's. All right, so here's a vector. Well, here's the start point and the stop point of a vector. And I want to find its position vector. And let's practice writing it both ways. Unit vector notation and then with the angle brackets. All right, so they call the points P1 and P2. Which one is the initial point?
P1.
P1, and the terminal point? P2. All right. So let's start with our formula. We need to do 3 subtractions. What is going to be my calculation to find the x component of the position vector? Yep.
4 minus -1.
4 minus -1. Okay. What's going to be the calculation to find my y-axis component?
6 minus 2.
6 minus 2. And the calculation for the z-axis component. So we get the x, we get the y, now we need the z. Yep.
2 minus 3.
2 minus 3. Has to be in that order. If you do it in a different order, it's not right. Okay. So what's going to be my final answer for my position vector? Yeah.
It's going to be
5, 4, -1. And that's if you write it in what our book calls that algebraic notation with the angle bracket. How would you write that answer in unit vector notation? Yep.
5i plus 4j plus, or minus 1 k.
Minus 1k or just minus k? Yep. So if you think of the i's, the j's, and the k's as building blocks, like if this represents an I, you're stacking 5 I blocks together, then you're stacking 4 j blocks together, and then you're stacking 1 k block that would like go into the board, and then you'd be connecting where you started, to where you stopped. And that would be what the vector looks like. So this one would go like behind the board. Okay. Any question on that? Okay, so that's position vector. Now we're going to look at all the same formulas that we did. I think it was Tuesday. Monday, well, maybe not Monday. That was Tuesday. For adding, subtracting, scaling, and finding the magnitude. But we're not going to do any of that visually. Okay? We're just going to use numbers. So I'm going to use 2 different vectors, v and w. Each vector has an x, a y, and a z component. And if I want to add the two vectors together, if they just had an x and a y component, that's what I would do. I would take x1 plus x2, y1 plus y2, and I'd be done. What do I have to put on the end of that if I'm adding vectors in 3D? What's the additional piece you need? Yep,
Z1 plus Z2.
z1 plus z2. And it works exactly the same for subtraction. So that's why I wrote plus or minus, just if you're adding or subtracting. Okay, so add the x components, add the y, add the z. If you're subtracting, subtract the x components, subtract the y, and subtract the z. With addition, the order doesn't matter, but with subtraction, it does. Just make sure you follow the order they tell you to follow. Okay, so that's adding and subtracting. The next one is when you put a number in front of a vector. Does anybody remember we had a name for that number? Anybody remember what that number was called? Yeah?
Scalar.
It's a scalar. Yep. So this is a scalar product. This is not dot product. This is a number times a vector. Dot product is a vector and a vector. This is a number and a vector, so it's different. And what are the things that can happen when you scale a vector? There's a limited amount of things that can happen.
It's smaller or bigger?
Okay, that's two of them. It can get longer or shorter. Yep. And it can flip. What kind of number would this have to be to make the vector flip around?
Negative.
A negative, yeah. It's a longer, shorter, or flip direction. Okay, when you scale a vector, we think of it as a distributive property. You multiply your x component by your scalar, your y component by your scalar, and what am I going to put underneath that box to extend the formula to 3D? Yeah? So what, can you tell me a little bit more detail? Yeah, the scalar, whatever that is, the number times z1. So it's alpha times x1, alpha times y1, alpha times z1. Right, now, last thing we're going to look at is when we take a vector and put those double bars around it. Okay, that's not absolute value, that's a single bar. What do the double bars mean?
Magnitude.
Magnitude. Yep. And what formula do we use in 2D that basically gives us the magnitude? Yeah?
Distance.
Okay, and the distance formula is really what?
Pythagorean.
It's really Pythagorean theorem. So in 2D, that's how you find the magnitude. You take your x component, you square it. Your y component, you square it. Add them up and take the square root. Now we're going to extend it to 3D. So what am I going to put?
Z1 squared.
I'm going to put z1 squared added on to what I already have, and that extends the formula to 3D. All right, so now we'll try a few of those, just adding, scaling, and finding magnitude. Okay, so let's try v plus w. Okay, so again, there's no visual. We're just going to add them up numerically. Since they gave us the problem in unit vector form, we'll write our answer the same way. Unit vector, I, j, and k. Okay, so v is 2i plus 3j minus 2k. And w is 3i minus 4j plus 5k. What's going to be my x-axis component if I add v and w together?
5i.
5i. Yep. So we get 5i How about my y-axis component?
Negative J.
A negative j. So that's like we've stacked 5 i's going to the right. We have a 1j down, and now I need to go, do I go in or do I go out of the board? Which way? So what's my z-axis component?
3K.
3k. So in that case, it would be like stacking 3 of them towards you. And that's how you add V and W in 3D. Any questions on that? Okay, so magnitude. This time you don't need W. You're just working with vector V. W is not a part of it. All right. Can anyone tell me what my calculation is going to look like when I set it up to find the magnitude of V? Yeah.
Would be square root something on the side.
Yeah, we need a big square root symbol.
2 squared plus 3 squared minus 2 squared.
Minus 2 squared?
Yeah.
No, it's not 2 squared plus 3 squared minus 2 squared.
Plus negative 2 squared.
Plus negative 2 squared. Yes. And that's different. Okay, so plus negative 2 squared. Okay. So when I simplify that, what am I going to end up with under the square root? Square root of 17. Yep. And that is your distance. Oh, no, I'm sorry, it's the length of V. Yep. Okay. Any question on how we got the magnitude of V? Okay. Let's try a scalar. So now I want to find 3W. 3W. All right, anybody think they can tell me what 3W would be? Ricky?
9I minus 12J plus 15K.
That's 15. Okay, perfect. Okay, what kind of answer is this last one? This is a what? Like, I'm thinking pretty kind of general here. What do you call this kind of thing? Nope, it's not an equation. Equation would have to have like a single variable, and then you have something on each side of an equal sign. But we don't really have any variables in 9i minus 12j plus 15k. We have letters, but they're not variables. So what is that? Yeah? Well, it's a scalar product. That's what we calculated. But what kind of an answer did we get? The answer is a
Coordinate?
no, it's not a coordinate. A coordinate would be a location somewhere. That's not a location.
Is that standard form?
Well, I guess it's the standard way that we write the thing I'm thinking of.
Vector.
It's a vector, yes. This is a vector, okay? A vector does not describe a location. It describes a direction, and it describes a length, how long something is. So if that was a vector for like an airplane, that would tell you how fast the plane is going, and it would tell you which way the plane is going. So that's a vector. What was the answer to part A? What kind of answer was that?
Vector.
That's also a vector. Yep. How about the answer to part B?
Magnitude.
It's just a magnitude, right? That is not a vector. This is just a number. That does not tell me any kind of direction. It tells me the length of something. So it's important to know what kind of answer you're getting when you're solving. All right. So the next thing we did was dot product. Now we just did dot product in 2D, so I'm not gonna put that back up. Let's see if we can figure out dot product in 3D. Okay. So anyone think they can tell me the first part of the calculation to find the dot product between V and W in 3D? Yeah.
Well, I would do x1 times x2.
Okay, so we're going to have an x1 times x2. All right. And what's going to come right after that?
Y1 times Y2
Nope, something before that.
plus.
Plus. And then y1 times y2. And if you were doing 2D, that's all you need. That's your dot product in 2D. What else do we need to make it 3D?
Plus Z1 times Z2.
Plus z1 times z2. Yep. And that's how you find a dot product in 3D. Okay, so let's find the dot product between those two vectors. 2i minus 3j plus 6k, and 5i plus 3j minus k. So just like we do in 2D, I would start by writing down the formula and then leave space for everything you got to fill in. Okay, what am I going to fill in my first two parentheses?
2 and 5.
2 and 5. Okay, in the next set, -3 and 3. And the last set,
6 and -1.
6 and -1. All right, so 2 times 5 is going to give me -3 times 3, and 6 times -1. So 10 minus 9 gives me 1, and 1 minus 6 gives me
-5.
-5. And that's how you find your dot product. Now, the last thing is the same thing we did with the dot product in 2D. What did we use the dot product to figure out? It was part of the formula to figure this out.
Wait, what was the question?
So what did we use the dot product to do yesterday? Connor, what did we use the dot product to do yesterday? We had to do this in every question in the homework.
Just to find the magnitude.
Well, finding the magnitude was something else we did. But the dot product specifically was part of this formula to do something. And the magnitude is also part of it. Yeah?
To find the angle.
To find the angle. Right? So to find the angle between two vectors in 3D, they're going to give you vectors just like that. And what was the trig function that we used when we were finding the angle? We used cosine. Well, the formula for finding the angle in 3D is exactly the same as 2D. There's no change to it. And the reason there's no change is because we've already changed each of the individual parts of the formula. It's a 3D dot product, which I just showed you how to do right up there. Then it's a 3D magnitude, which I showed you how to do right here, and another 3D magnitude. But the formula itself is exactly the same structure. Cosine of theta equals the three-dimensional dot product over the three-dimensional magnitude times the three-dimensional magnitude. It's just not two-dimensional. Right? So when you've got two vectors in 3D, if they were on the board, like think of that's how we would do it before. Well, now in 3D, you can take that vector and rotate it off the board. But you're still finding the angle between the two vectors. That's all you're doing. All right, since we already have the dot product for the last problem, I'm going to find the angle between these two vectors because we're already partway done. So we've got 2i minus 3j plus 6k, and 5, 3, negative 1. 5, 3, negative 1. Okay. What did we get for the dot product? We got negative 5. So that's already done. Now the magnitude of v. Right, so now we want to do what we just did in example B for the problem a couple problems ago. So we got square root and remember you've got 3 different components. They're all going to be added together and squared. Okay. What are the numbers I'm going to fill in when I find the magnitude of u? Yep.
2, negative 3 and 6.
2, negative 3, and 6. Okay. Set it up exactly the same way for the magnitude of v. And what am I going to fill in for that formula? Yeah, Dylan?
5, 3, and negative 1.
Okay, so we got 5, 3, negative 1. Now we just need to simplify those and see what we got. So I have a little more space. I'm going to move this. I didn't want to move that. Okay. All right, let's do that up. 2 squared is going to give me how much? So I get 4, negative 3 squared, and 6 squared. What's 4 plus 9 plus 36? 49. And then the square root of that? 7. Okay, so there's the magnitude of u. And lastly, we need magnitude of v. What's 5 squared? 25. And 3 squared? 9. And negative 1 squared? Okay. This one will not come out to a number you can take the square root of, so we'll just leave it. We're going to get the square root of 35. Okay, so now have we figured out what they wanted? No, we haven't done what they wanted yet. We have all the pieces we need, but what is it that they want us to figure out? They want the angle. Right, so using those 3 pieces, what's my formula on the left side of the equation to find the angle?
Cosine theta.
Cosine theta. Put that on the left. And what's going to go on the right? Dot product in the top. So negative 5. And the product of the magnitudes in the bottom. Okay, so there's our equation. We still haven't done what they wanted, though. We haven't found the angle yet. So now you need to solve. To solve it, we need theta alone. How do we get theta by itself? Gabe, how do we get theta by itself here?
The inverse.
Yep, I'm going to take the inverse cosine on both sides. Good. So that cancels. And now we're going to type that in, but because the denominator has a product, which it always has a product, we need to make sure we put that in parentheses. Let me show you what happens if you don't. You'll get something that is not right. 7 squared divided by 7. Why is that? Oops, what was that? -5 divided by 7 square root 35. So in that case, you get 147.688. But that's, oh, I didn't even put the 7. Sorry. Let me put in the 7. And we got lucky in that case because it actually gave me an error. It might not give, depending on the number, it might not give you an error. Right? Like if you had a bigger number here, like 75, well, that's even worse now because you might think that's right because it gave you a number, but that's completely wrong because it didn't do what you really wanted. What you need to make sure is you put the denominator in parentheses. Okay? And I'll do this with just the 7 in a second. But I want to show you, by putting it in parentheses, you do get a completely different answer. All right? It's not even close to being the same. So let's plug in ours and do it in parentheses the correct way. So I have -5. I think the calculator, or maybe I did that, put an extra parenthesis around the 35. You could keep that there, but you don't need that. Right? What I've typed in right there, that's perfect. The extra parentheses around the 35 won't hurt anything. And that is the correct answer. Okay, so make sure you put parentheses around the denominator. 96.93. Okay. Any question on that? So that really pretty much reviews everything that we did during the week. On your reference sheet, if you're going to put formulas on it, you really don't need to put the 2D formula and the 3D formula. If you just put the 3D version of every formula, it automatically will work for the 2D version. Just don't look at the Z part, and that's the 2D version. All right. So that is the homework for tonight. The part that I just erased, that is what's called a cross product, which is not something that we're going to look at. Okay. So make sure if you look at the video, look at the one from YouTube because that's up to date. In video on Schoology, it might have the cross product. Okay, so I'll leave that up, and in the last 5 or 6 minutes, I will put all the topics that are on the test.
The test is tomorrow.
Yes, test is tomorrow, and I will be after school today in case anyone needs extra help.
Jen.